Welcome to this walkthrough of problem number 6, Zigzag conversion. In this session, we'll explore an interesting string manipulation problem that challenges both your algorithmic thinking and attention to detail. Let's dive in and uncover the best way to solve it effectively. The problem is about converting a string into a zigzag pattern based on a given number of rows and then reading the characters row by row to form the final output. For example, the string PayPalishiring can be arranged in 3 rows as shown in the diagram. Notice how the letters zigzag down and then back up repeatedly, forming a pattern. After arranging the string in this way, you read each row from top to bottom, resulting in the output PHNPLSIGYR. Your task is to write a function that performs this conversion. The input consists of a string S, which can include uppercase and lowercase letters, digits, and special characters, and a positive integer number rows, which specifies the number of rows. The length of the string is between 1 and 1000, and the number of rows is at least 1 but not more than the length of the string. The output of your function should be a string that represents the characters in the zigzag pattern read row by row. Let's look at an example to clarify this further. If the input string is PayPalishiring and the number of rows is 3, the output should be PHNAPLSIGYR. In this case, the zigzag pattern is formed by placing the letters in 3 rows. As you can see, the first row contains P, A, H, and N, the second row contains of P, L, S, I, and G, and the third row contains Y, I, and R. Reading each row in order, we get the output string PHNAPLSIGYR. Now, let's consider another example with the same string, PayPalishiring, but this time with 4 rows. When arranged in a zigzag pattern with 4 rows, the letters fall into a different arrangement. The first row has P, I, and N, the second row has a L, S, I, and G, the third row has Y, A, H, and R, and the fourth row has P and I. If you read these rows line by line, you get the output string PNLSIGYHRPI. This demonstrates how the arrangement changes depending on the number of rows specified. In the case of a single row or very short strings, the zigzag pattern simplifies dramatically. For example, if the input string is at and the number of rows is 1, there's no zigzag pattern to create. The input string is simply the output string. Similarly, if there's only 1 row specified, the output will always be the same as the input, as there's no opportunity for characters to zigzag. This makes these cases straightforward to handle. Finally, there are a few edge cases to consider. If the input string contains only 1 character, such as S equals A, the output will always be the same as the input, regardless of the number of rows. If the number of rows is 1, there's no zigzag pattern, and the output is identical to the input string. On the other hand, if the number of rows is equal to the length of the string, each character will occupy its own row, and reading line by line again results in the same string as the input. For longer strings, such as S equals ABCDFGHIJKLMNOPQRSTUVWXYZ, it's important to ensure the zigzag pattern is constructed correctly and that no characters are skipped or misplaced when reading row by row. These considerations will help ensure your solution handles all possible inputs effectively. To solve the zigzag conversion problem, one approach is to explicitly construct the zigzag pattern row by row, which we call the brute force approach. Here's how it works. We first create a list of strings, where each string represents a row in the zigzag pattern. The number of rows is determined by the given input number rows. As we traverse the input string character by character, we use a variable, current_row, to keep track of which row we are currently filling. Additionally, we use a direction flag to decide whether to move downward or upward within the zigzag pattern. When we reach either the topmost or bottommost row, we reverse the direction. After we've processed all characters, we simply concatenate all rows to form the final result string. This approach has a time complexity of O(n), since we visit each character once, and a space complexity of O(n) to store the rows. However, while this method is straightforward, it requires additional space for the rows and involves managing the direction flag, which can make the implementation slightly more intricate. Alternatively, we can use a more optimized approach based on direct index mapping. Instead of explicitly constructing rows, this method calculates the zigzag row for each character directly from its index in the string, avoiding the need for extra storage. The key observation here is that the zigzag pattern repeats every 2 number rows, 2 characters, which corresponds to 1 complete downward and upward movement. Using this periodic structure, we can determine the row index for each character. The process involves creating an empty list for each row, then iterating through the string and calculating the row position for each character based on its index and the periodicity. We then append the character to the appropriate row and, once all characters are placed, join the rows to generate the final result. Similar to the brute force method, this approach has a time complexity of O(n). However, while it reduces the conceptual need for building rows explicitly, it requires careful handling of the row index calculations, which can make the implementation more complex. For this problem, we opted for the brute force approach that involves row-wise traversal and explicit row construction. This strategy stands out for its simplicity and ease of understanding, which makes it ideal for implementation and debugging. The time complexity is O(n), which is optimal, and the space complexity is manageable for typical constraints, such as a string length of up to 10 to the power of 4. When comparing the two approaches, the brute force method is slightly less efficient in terms of space usage but is significantly more intuitive than the direct index mapping approach. While the optimized approach is better suited for scenarios where minimizing auxiliary space is critical, it introduces additional complexity that may not be necessary for most practical cases. The periodic structure of the zigzag pattern, which repeats every 2 number rows, 2 characters, was a key insight that simplified the placement logic. Still, the brute force method of building rows explicitly provides a clear and practical solution. Ultimately, we chose the brute force row building method due to its balance of simplicity, clarity, and efficiency. This approach not only satisfies the problem requirements but is also straightforward to implement and verify. While the optimized method could be more space efficient, the additional complexity it introduces was unnecessary for this problem. By leveraging the straightforward nature of explicitly building rows, we arrived at a solution that is both intuitive and effective, making it the best choice for this scenario. To solve the zigzag conversion problem, the goal is to rearrange the characters of a given string S into a zigzag pattern across a specified number of rows, and then read the characters row by row to produce the final output. The zigzag pattern alternates between moving downward through the rows and then upward back toward the top, creating a zigzag traversal. One way to approach this problem is by explicitly building the rows of the zigzag pattern step by step. First, we initialize the necessary data structures. Specifically, we create a list of empty strings called rows. Each string in this list will represent one row of the zigzag pattern, and the size of this list is determined by number rows. To track our current position in the zigzag traversal, we use a variable current_row, which starts at 0. Additionally, we use another variable direction, initialized to 1, to help us decide whether to move downward through the rows or upward back toward the top. These simple structures lay the foundation for implementing the zigzag logic efficiently. Once the data structures are initialized, the next step is to traverse the input string character by character. For each character C, we append it to the string corresponding to the current row, which is tracked by rows, current_row. After placing the character, we need to determine the next row to process. This is where the direction variable comes into play. If we are at the topmost row, where current_row is 0, we set direction to 1 so that we start moving downward. Conversely, if we reach the bottommost row, where current_row equals number rows 1, we set direction to -1 to begin moving upward. Then, we update current_row by adding direction, effectively moving to the next row in the zigzag traversal. Finally, after all characters have been traversed and placed into their respective rows, we combine all the strings in the rows list into a single string. This concatenated string becomes the result, representing the zigzag pattern read row by row. Understanding the key insights behind this approach can help us appreciate its simplicity and efficiency. First, the zigzag traversal relies on alternating movement between downward and upward directions. By managing this with a direction variable, we eliminate the need for complex conditionals, making the logic clean and easy to follow. There are also a couple of edge cases to consider. If number rows is 1, the zigzag pattern reduces to the original string itself because there's no vertical movement. Similarly, if the string is shorter than or equal to the number of rows, each character will occupy its own row, and again, the result will be the input string. From a space complexity perspective, the rows list requires O(n) space, where n is the length of the string. This is because, in the worst case, each character is stored in its own row. The use of simple data structures like the list of strings for rows, along with the current_row and direction variables, ensures that the solution is both intuitive and efficient. Analyzing the complexity of this approach, the time complexity is O(n), since each character in the input string is processed exactly once during the traversal. The space complexity is also O(n), because we store the characters in the rows list, which grows with the length of the string. Let's illustrate this with an example. Suppose the input string is PayPalishIring and number rows is 3. We initialize rows equals, current_row equals 0, and direction equals 1. As we traverse the string, we append each character to the appropriate row. For instance, the first character P goes to rows 0, then we move to row 1 for A, and row 2 for Y. At this point, we reverse direction and move upward, placing P in row 1 and A back in row 0. We continue this process, alternating the direction whenever we reach the top or bottom row. After processing all characters, the rows become PHN, APLSIG, YR. Concatenating these rows produces the final output, PHN APLSIG YR. This implementation solves the zigzag conversion problem efficiently. The convert function takes a string S and an integer number rows as inputs. First, it handles edge cases where the zigzag pattern is unnecessary. If number rows is 1 or greater than or equal to the length of S, the string is returned as is. Next, the code initializes a list called rows, where each element represents a row in the zigzag pattern. Each row starts as an empty string. The variables current_row and going_down are used to track the current position in the zigzag pattern. Current_row keeps track of which row is currently being filled, while going_down determines whether the movement is downward, toward the bottom row, or upward, toward the top row. The main logic iterates through each character in the input string S. For each character, it appends the character to the current row. If the code reaches the top or bottom row, it toggles the direction by flipping the going_down variable. After processing the character, it moves to the next row, either incrementing or decrementing current_row depending on the direction. Finally, the code concatenates all the strings in the rows list and returns the result. This efficient approach ensures that the zigzag pattern is built in linear time, making it well-suited for the problem's constraints. Here, we begin by defining our solution class and the convert method, which takes a string S and an integer number rows as inputs. The first condition we handle is a straightforward edge case, if there's only one row, or if the number of rows is greater than or equal to the length of the string, we can simply return the original string as there's no zigzag pattern to form. Next, we create an array of string builder objects, one for each row, to store the characters of the zigzag pattern. Using a loop, we initialize each element in this array with a new string builder instance. We then declare two variables, current row and going down. Current row keeps track of the current row we're populating, and going down is a boolean that toggles the direction of movement downwards or upwards through the rows. After that, we iterate through each character in the string. For each character, we append it to the appropriate row in our string builder array. If we are at the topmost or bottommost row, we toggle the going down variable to switch the direction. Then, we update current row accordingly, either incrementing or decrementing it based on the direction of movement. Finally, we consolidate the results. A new string builder object, result, is created to hold the output string. We loop through each row in our string builder array, appending its contents to the result. This combines all the rows into one continuous string while preserving the zigzag order. At the end, we return the string representation of the result string builder, which gives us the final zigzag converted string. This approach is efficient and ensures that we correctly handle the zigzag traversal of the rows. Here, we are solving the problem for the input string PayPalishIring with 3 rows. First, we handle the edge case. Since the number of rows is greater than 1 and the string length is greater than number rows, we proceed with the algorithm. Next, we initialize an array rows with 3 empty strings, one for each row, and set current_row to 0. The going_down flag, which helps us track the direction of travel, is initially set to false. Now we iterate through each character of the string. Starting with P, we append it to the first row, update rows to P, and change direction to move downward. we increment current underscore O to 1. The next character is added to the second row, resulting in rows equals P. Again, we increment current underscore O to 2. Then, the character Y is added to the third row, updating rows to P of Y. Since we've reached the bottom row, we toggle the direction upward by setting going underscore down to false and decrement current underscore O back to 1. Following this zigzag pattern, we process the remaining characters, filling the rows until we get rows equals PHN, APLSIG, YR. Finally, we concatenate the rows to form the result string, which is PHN, APLSIG, YR. Now, let's consider the input string ABCD with 2 rows. Since the conditions are met, we proceed with the algorithm. We initialize an array rows with 2 empty strings and set current underscore O to 0. The going underscore down flag is initially false. Starting with the first character, we append it to the first row, updating rows to We change the direction to move downward and increment current underscore O to 1. The next character, B, is appended to the second row, resulting in rows equals B. Since we've reached the bottom row, we toggle the direction upward by setting going underscore down to false and decrement current underscore O back to 0. Following the same pattern, C is added to the first row and D to the second row, giving us rows equals AC, BD. After concatenating the rows, the result is ACBD. For the final example, where the input is hello with only one row, no zigzag pattern is needed. The algorithm directly returns the input string as the result, which is hello. This case demonstrates that if there's only one row, the output is simply the original string. To analyze the time complexity of this solution, we start with the initialization of the rows. Here, we use a list comprehension to create a list of number rows empty strings. This operation runs in O, number rows, time because it iterates once for each row. Next, we move to iterating through the characters of the input string S. For each character, we append it to the current row, which takes O1 time if the strings are relatively small. Then, we check whether we've reached the top or bottom row to adjust the direction. This involves a few constant time operations like comparisons and assignments, all of which also take O1 time per character. Updating the current underscore O variable with simple arithmetic similarly runs in O1. Since these operations are performed for each of the len, S, characters in S, the total time complexity for this step is O, lens. After processing all the characters, we concatenate the rows to form the final zigzag string. This concatenation is achieved using the join method, which iterates over all the characters in the rows list. Since the total number of characters in rows matches the length of the input string S, the join operation takes O, lens, time. Now, when we combine all these steps, we have the initialization step taking O, number rows, the iteration over the string taking O, lens, and the final concatenation also taking O, lens. Because len, S, is typically much larger than number rows, the overall time complexity simplifies to O, lens. Next, let's examine the space complexity of this solution. The key contributor is the rows list, which is initialized with number rows empty strings. As we process the input string, characters from S are distributed across these rows. In the worst-case scenario, every character in S will be stored in the rows list. This means the memory usage for rows is proportional to O, lens. Beyond the rows list, we also use a few auxiliary variables, such as current underscore O, going underscore down, and the loop variable char. These variables require a constant amount of space, or O1. Therefore, the total space complexity of this solution is O, lens, dominated by the memory needed to store the rows. Now, let's analyze the best, average, and worst-case scenarios. In the best-case scenario, if number rows is 1, the zigzag pattern is irrelevant since there's only one row. The function simply returns the input string without any additional processing, leading to a time complexity of O1 and space complexity of O1. For both the average and worst-case scenarios, where number rows is greater than 1, the time complexity remains O, lens, due to the iteration and concatenation steps, and the space complexity is still O, lens, due to the storage of rows. Comparing this optimized solution to a brute force approach, the latter might involve explicitly constructing the zigzag grid, requiring additional space proportional to O, number rows *lens, and potentially more time for assembling the result. The optimized solution avoids these inefficiencies by directly appending characters to rows and concatenating them at the end, making it both time and space efficient. Finally, let's consider the optimality of the current solution. This approach minimizes redundant computations and avoids unnecessary memory usage by appending characters directly to the appropriate rows as we iterate through the input string. The concatenation step at the end is efficient and avoids the overhead of simulating a full grid. To mathematically confirm the big O complexity, let's denote the length of the string as n. Iterating through all characters takes O, n, and concatenating the rows also takes O, n. The initialization of rows depends on number rows, which is negligible in comparison to n. Combining these, the overall time complexity is O, n. Similarly, the space complexity is O, n, as the rows list is the only significant contributor. This makes the solution optimal for both time and space, effectively handling the zigzag conversion problem with minimal overhead. When working with the zigzag conversion problem, there are a few common mistakes to watch out for. One major issue is incorrect index management during the zigzag traversal. If you forget to reverse the direction when reaching the top or bottom row, the rows will be built incorrectly, resulting in an invalid zigzag pattern. For instance, the traversal might overflow beyond the designated number of rows or fail to switch directions at the right time. Another frequent mistake involves mismanaging row initialization. If you don't initialize the correct number of rows as empty strings or lists before the traversal begins, you may encounter runtime errors or incomplete results because the program tries to add characters to rows that don't exist. Finally, overcomplicating the brute force logic is another pitfall. Some solutions use nested loops or unnecessary data structures to simulate the zigzag traversal, but this adds unnecessary complexity to the code, making it inefficient and harder to debug. Simplifying your approach can help avoid these issues. Another area where mistakes are common is in handling edge cases. For example, when the number of rows is 1, or when the number of rows is greater than or equal to the length of the string, these scenarios require special attention. The expected result in such cases is simply the input string, so failing to account for these can lead to incorrect outputs or wasted computation. Additionally, inefficient string concatenation is a frequent inefficiency. Using the plus equals operator within a loop to concatenate strings can be problematic because strings are immutable in many languages, such as Python. This approach can lead to an O(n) squared time complexity due to repeated string copying. A better alternative is to use efficient methods like .join in Python or equivalent techniques in other languages to improve performance and maintain scalability. In interviews, there are a few key insights to keep in mind for this problem. First, it's important to recognize that the zigzag pattern relies on periodic traversal of rows, and this periodicity can simplify your calculations when implemented correctly. Showing that you understand this pattern is a good way to demonstrate problem comprehension. Equally important is being proactive about edge cases, such as single rows or very short strings. Addressing these upfront not only ensures the correctness of your solution but also signals to the interviewer that you're thorough and efficient in your problem-solving approach. Discussing space versus time trade-offs is another valuable point. For example, you may want to clarify whether using additional space, such as lists for row storage, is acceptable, or if an in-place solution is preferred. Finally, always strive to explain your intuition clearly. While brute force approaches can be simpler to describe, discussing more optimal solutions, such as direct string manipulation without explicit row tracking, can highlight your depth of understanding and ability to optimize. There are several related problems and alternative approaches worth exploring. Zigzag conversion itself is often considered the foundational problem for understanding zigzag traversal. Beyond this, problems like group anagrams require efficient string manipulation and grouping logic, which overlaps conceptually. Letter combinations of a phone number involves careful management of combinations, which is somewhat similar to the zigzag traversal. Additionally, encode and decode strings focuses on handling strings and patterns, particularly encoding and decoding logic, making it another relevant problem to practice. In terms of approaches, the row-based tracking method, often called the brute force solution, is a common starting point. It's straightforward to implement and debug but requires O(n) additional space to store rows. On the other hand, direct index calculation avoids this extra space by computing the zigzag positions directly. While this can improve space efficiency, it's a bit more challenging to implement and can lead to errors if not handled carefully. For those looking to push for even greater optimization, in-place string manipulation is an advanced technique worth mentioning. By modifying the string directly, this approach minimizes space usage completely. However, it comes with significant trade-offs. The complexity of implementation increases dramatically, and it can become impractical for interview scenarios where clarity and correctness are often prioritized over squeezing out every ounce of optimization. Unless specifically requested, sticking to row-based tracking or direct index calculation usually strikes the best balance between simplicity, efficiency, and maintainability. Each of these methods offers insights into different aspects of problem solving, so choosing the most appropriate one depends heavily on the context and constraints of the task at hand. Great job! We've broken down problem number 6, zigzag conversion, and reviewed a structured solution approach. Remember, practice is key to mastering algorithmic challenges. If you found this helpful, consider subscribing to stay updated with more lessons like this. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!